Hello, my name is Sam Pluta, and I'm the author of the RTNeural Plugin. This is a real-time cross-platform neural inferencing external for Macs, PD, and SuperCollider on macOS, Linux, and Win32. It's based on Jatin Chowdhury's open source RTNeural inference engine. So I did not make the inference engine. That's an open source project by Jatin. And I just made the externals and the help files and some of the Python stuff. So what are the goals of this project? One is to create a general purpose inferencing platform for SuperCollider, PD, and Macs that runs at both audio rate and control rate. It has to be real-time safe, which is a must for audio. Things like libtorch are not at this time real-time safe, so using something like RTNeural as the inferencing engine is a necessity to make things work in real time. The goal is to be able to load any shape of neural network, not just an MLP or an LSTM, which is what most of the examples are. But the goal is in the end to have an if you train it, it will run kind of inferencing engine. This uses Python for training, not my own training system. It will load PyTorch and Keras trainings. These tools have gotten insanely good over the last 5 years. You know, there's like billions of dollars being spent on them, so why not use them? So if Python can train it, and then if you can save it into RTNeural format, you can load it. So RTNeural is looking for Keras format training. So when you train in PyTorch, you need to convert it to Keras. And I've provided tools to do that for many shapes. This allows us to tap into myriad developments in Python land. And since we can't beat them, we must join them. Finally, audio trainings take a long time, many hours or days. So another goal of this is something like an audio training. You don't want to be running that training in, PD if you want to be using PD for creative coding. So you can kind of set up a Python instance on the terminal in the background and run it. You can even run it on the GPU. And in that case, it's, it probably won't mess with your creative work unless it's video. So you can also do trainings on Google Colab or something like that and run it, on the web. So more goals of the project. So it's an inferencing engine. It loads many kinds of NN layers. So this is the work of the open source inferencing engine, but they can load dense layers, GRU layers, LSTM layers, conv1, conv2d, you can read, and many different kinds of activations, TANH, ReLU, sigmoid, which are the most common ones, and then these other ones. Anything that RTNeural inferencing engine supports, the plugin can do. And the question is, why not libtorch or Onyx runtime? Like I said, libtorch is not real-time safe. Onyx runtime is real-time safe. It's just way less efficient. So it's 10 to 40 times less efficient found on certain, models. And so that's really unacceptable for audio. I may add that functionality in the future. I did make an Onyx engine in the past, and that would not be difficult to do. I could really just add it into this plugin and make a plugin that does all of the above. Should not be difficult. So things that the plugin can do: multi-layer perceptrons for control rate or audio rate inference. It can run at control rate, so doing the classic Wekinator or fluid MLP regressor stuff. It can also be run at audio rate. Or at audio rate with triggers. So this was a feature request, is that it can run a multi-layer perceptron at audio rate and get a trigger that's at audio rate and be sample accurate by audio rate, but only be doing inferencing every so often. For LSTM and GRU models, you can do audio rate distortion effects like loading Proteus and I2X distortion models. You can train guitar pedals, distortions, compressors, tubes, anything that has an input-output. So can't really deal with delays with these as of yet, but maybe that will change in the future. Because models might be trained at a sample rate, RTNeural does internal resampling using libsamplerate. So it doesn't matter what sample rate you do your training at, what kind of audio you do your training at, your models will work at any sample rate. So this is something that was actually very difficult. So if you're running, your computer is running at 48K, but your training was done at 44.1, you can load the 44.1 model, and then what will happen internally is it will get the block of audio at 48K, it will convert it to 44.1, it will do the inference, and then it will convert it back to 48K. And you don't have to think about it. All you need to do is tell RTNeural what sample rate the model was trained at. So all the SC, Max, and PD builds for Windows and Mac are available from the Releases tab of the GitHub page. So if you go to github.com/spluta/RTNeural_plugin, that's the main GitHub page. Linux people, you got to do the build yourself, but you're used to it. All the instructions are there. It's pretty straightforward. Windows and Mac, under the Releases tab on the right-hand side of the page, there should be builds, current builds for whatever platform you need. So now there's going to be a tutorial on different ways to use this project. There are lots of ways to use this project that I'm not doing. I think one of the things about machine learning and AI things is we know what these neural networks can do, but we don't necessarily know how to apply them. And so I've come up with some applications. Some are silly, some are really useful, and some are things that people are doing very actively in the field. But there's also things that people haven't thought of, and I think that that's where most of the potential of this plugin and others like it are. So if you think you might want to try to make a new kinds of training, then go for it, because it might be possible. Okay, I'm going to show you how to download and install the RTNeural package. So I'm going to go to github.com/spluta/RTNeural plugin. And here is the repository with all the code. It gives you instructions on how to build things, etc., etc. You don't really need that. What you should be able to do is just use one of the release builds, though we're going to look at something here in a second. So if I go into all builds, I'm going to download, I'm on a M1 Mac, so I'm going to download the Max PD SuperCollider, and I'm also going to download the RTNeural Python directory. Now, that one you want no matter which one of these you're using, because it's where all the Python magic happens. So I'm going to go back here because I'm going to need this in a second. Yep. And first of all, I'm going to look at the RTNeural Python download. So if I unzip this folder can go anywhere. For now, just for convenience of this video, I'm going to put it on my desktop. But it can go anywhere. It can go in your documents folder. It could go in your downloads folder. It doesn't really matter. So if I open this up, there's a number of directories and a bunch of different examples. A wavetable, a 4 wavetable oscillator trained on a multi-layer perceptron, a bunch of models that were converted from automated guitar sampling, automated guitar amp modeling library. You can find those models all over the internet. Some Jayton Chowdhury models. RTNeural inference engine is in fact his inference engine, so just a couple that were found in his plugins. This one doesn't quite work. And then MLP control, which can use a multi-layer perceptron as a control network. So the first thing I'm going to do is create a virtual environment. So you want to open up Terminal. And in terminal, we want to go to this directory. So I'm going to cd, change directory to RTNeural Python, and just drag that in, and it should say RTNeural Python. Now my Python here says base. What I want to do is I want to make a virtual environment. So in order to do that, I type Python -m venv, and what that means is I'm going to use Python to make a virtual environment, and my virtual environment will be called venv. And notice when I do that, it creates this folder in the RTNeural Python folder, and it took a second to do that because now there's a bunch of files in here. So by default, I'm not in the virtual environment, so I want to get into the virtual environment. So I'm going to say source. This is on Mac. On Windows, it's a little different. Source venv bin activate. So we're going to activate our virtual environment, and notice over here now it says venv. Yours might look a little differently, but as long as it changes and now we're inside of a virtual environment, that's what you want. So if I want to run some Python code within the virtual environment, first thing I need to do for RTNeural is I need to install some dependencies. So if you look in the README file, it says that some of the dependencies are keras, TensorFlow, and pytorch. Those are the ones we really need, and they're the ones we need at least to start with. So you can install them all in one line. Pip install torch keras TensorFlow and it's going to install all these packages. It'll take a second, not too long. Great. So once these are installed, you can look in here, and in the lib, there are now a bunch more things. And in the, sorry, that was the bin. And in the lib, there are a bunch more things. So we just downloaded and installed those things. So now we have pytorch, we have keras TensorFlow, and we have keras and TensorFlow installed in our virtual environment. And so if we want to try it out, a good one to try it out on, now this one takes a really long time. It's a pretty complex training, but we can try it out on this 4OS NLP torch. So this is uses PyTorch to train a multilayer perceptron to be basically a wavetable oscillator. So you can look in here if you want to play around with it, and we have here's the model. It's a multilayer perceptron, and we create basically a wavetable, 4 wavetables. And so what the neural network is going to learn to do is that it's going to get a ramp in, and then a second value. When the value is 0, it should output a sine wave. When the value is 0.3, it should output a triangle wave. When it's 0.6, it'll output a square wave. When it's 1, it'll output a sawtooth wave. This training takes a very long time, and I'll show you how to do it. But we would say Python, and then we can just drag this file in and let it go. And if we've installed everything correctly, this should work. It is working. This takes a long time to train correctly. It takes something like 50,000 epochs. That's not going to work for this video because it takes like all day. Something that's really cool is it is training on the GPU. So if we look in here, the Python is running mostly on the GPU. So that's kind of fun. Great. So I'm going to stop that because it doesn't make sense for us to actually run that training right now, but it means that our virtual environment has been installed correctly. Okay, now that we have the RTNeural Python virtual environment set up, I've got it over here in my terminal. We can look at an example in Max. So if I open up the RTNeural Max folder, so this needs to go into the Max library. So I have that right here. So basically in Max, I'm using Max 8 and in the library. So this entire folder should go in there. And we need to do something. We can do it in our terminal here. So we need to dequarantine the externals. This is an Apple annoyance, but in the README there is a it shows you one of the things you need to do. One of the things you need to do is code sign the plugins. So if I just copy this, code sign force deep S dash with a space after, and then don't need that, and then drag this external in, and it'll say replacing existing signature. And then we want to do it again, but for the tilde object, so for the audio rate object. So once you do that, then you also have to do the other one, XA, Xatter, C, and then do that with the tilde one. So you have to dequarantine and code sign the two externals. Not so bad. So now if we open up Max, we should be able to, yeah, it's already got the example opened up. Yeah, and I'm going to keep this one open. So if you needed to, you could just test it by making an RTNeural object, and as long as it doesn't go orange and give you an error, and then an RTNeural tilde object. And that one it's also happy with. So we've got this is the example from that comes with RTNeural. And so, this is a classic MLP example, multi-layer Perceptron example, similar to the Flucoma one. So if I just press load model here, it's going to load the model that is in the that's in the path of Max. So it's this model that is already in the examples. So saved models, MLP synth RTNeural JSON. So this is the one that's saved. This is what that file looks like. And this is the RTNeural format for a JSON file. And if we move this over here, it's moving around quite nicely. So what's actually happening? So this is a XY. The XY is giving values between 0 and 127. We don't want that. We want values between 0 and 1. So we're dividing by 127. And then we're packing those into a 2-element list, and we send those to RTNeural. So if a model is loaded, that's all you need to do. You just send it to an element list. Now the RTNeural object, see here, it says RTNeural 213. That means that it has 2 inputs and 13 outputs. This model is also trained on 13 outputs. So yeah, so it's getting the two inputs in, and it's giving us 13 out, which happen to be this fader bank right here. So if we want to, and it's coming out as a list, let me just show you. Great. Yeah, 13 values coming out as a list. So if we want to retrain the network or train a new network, we want to first clear all the points. Now it doesn't have any points. If I look over here, inputs, outputs, no, there are no inputs, input anything in the input array, and there's nothing in the output array here. So, but I'm still going to clear my points, post them. There's nothing there. Great. We want to make sure that the network is bypassed, because we don't want to be running inference. If it's not bypassed, I won't be able to set values down there to train it. So we're going to bypass it. Now what's happening when I move this and when I move these, all that's happening in this little subpatcher is it's setting a message box with 2 points and setting a message box with 13 points. So if I make those visible and move these around, it's moving those. And if I move these around, it's moving those, right? Setting those points. So when I press this bang button, it then sends those to RTNeural to add them as points. Prepend add input, prepend add output. So it'll add this point and add this point to an internal list that's internal to the plugin. So I cleared my points. I am bypassed. Now I'm just going to make some really obvious shapes. So how about that shape? And I'm going to add that point. And now this shape, I'm going to add that point. What's another obvious one? How about this? Add the point, and this. Add the point. So if I post my points, I have point 0 is 0, 0, which is this is 0, 0, point 1, 0, 1, point 2, 1, 1, point 3, 1, 0. And then these are the vectors that are the outputs. So those are the 2 things that the neural network needs to know in order to make a training. It also needs to know how many epochs it's going to do for a training. This can be much smaller than 5,000. I just want a very accurate training. Set the initial learn rate. It uses an atom optimized learn rate, so that is the initial learn rate, but it'll optimize it. Now we can set the layer data for the model however we want. We just need to we do want 13 outputs, so we have a hidden layer of 5 with a RailU activation function, hidden layer of 20 with RailU activation function, hidden layer of 13 with sigmoid activation function. So you're going to want a sigmoid on the output, but RailUs in the hidden layers tend to work pretty well. So great. So sorry, just going to make sure I did those, and I'm going to write a JSON file. This JSON file can go anywhere, and I'll just put it on the desktop. So I'll call it my training.json, save. So the JSON file is saved with the data. If we look at that file, it should be on the desktop. Yeah, so notice the file has epochs 5000, invals, the ones that we added, layers data 5, 20, 13 with a sigmoid, learn rate 0.001, and then the outvals, which is an array of arrays. Excellent. So now that we have that saved, we can do our training. And we do that in the terminal. So notice here in the help file, it says after the model data has been saved to a JSON file, it's ready for training. This happens in Python from the RTNeural Python directory, which is where we are here. So we just need to go to the root directory of the RTNeural Python folder. Yes, run Python. So I can even open this up, copy here, Python MLP control train convert .py f. So what is that? And then your file. So what does that mean? So this is going to run in Python. It's going to run the script MLP control train convert .py. So if you look in the RTNeural Python folder and we look in MLP control, there is this file, which does everything we need to do to train and save the file in the correct format. So yeah, if we look at it real quickly, it loads all of our all of the libraries that we need, and then it sets up a PyTorch model. It's going to train on the GPU if it's available, and then it trains it here, and then it makes a Keras model with the exact same shape, and then it saves it as a Keras model, because RTNeural inference engine really can only load Keras models. So Python, and then MLP control / MLP control train convert, and /F. And now all I need to do is drag in my file. So hopefully I can remember where that was. And I know where it was. It was on the desktop. The F means the file that that's gonna contain the JSON. So if I run that, the first time you run it, it's going to take a little longer. That's a Python thing. It just takes a little while to get going, as you can see here, taking its sweet time. Okay, so you can see that it made the network. It's training it for 5,000 epochs. It is very, very accurate. That is very accurate, and there's very little loss. So that's nice. It will then tell you that what the training loss was, and it'll show you a PyTorch tensor output and a Keras tensor output. And then it should say the predictions are the same. Something that's set up here, Onyx export failed. If you want to export the model in Onyx format, install Onyx script with pip. So let's just do that real quick. Pip install Onyx script. And we'll just run the training again. Notice this time it was much, much faster. And now you should have your original JSON file, a PyTorch file, an Onyx file, and an RTNeural file. These might be useful in the future. Maybe you make a training that you don't want to do again, but you want to load into PyTorch and you want to load into Onyx script or Onyx runtime, then you can do that. So if I then go over here and say load model, and I am going to load my training. Now, if I unbypass, it's very much what I just trained the network to do. So the thing to do then is, well, what do you want to do with this this data? And you basically have 13 sliders that you can use to do it whatever you want. So this is a help file, and we opened it up, and it trained on 2 inputs and 13 outputs. Well, what if we want it to be on 4 inputs and 10 outputs? Well, we can pretty easily make that change. We're just going to go into RTNeural. We're going to say 4, 10, and I am going to move these over here. And I'm going to duplicate this. Make my pack deal with 4 points, not 2. Great. So I'm going to edit this mammer jammer to have 10 sliders, not 13. And okay, so I'm going to clear my points. I'm going to bypass. And I am going to set something here. I am going to add that point. Let me see here. Yeah, there's 4 values and 10 values coming out. So let's see if I post the points. Yeah, we have a point that is 4 inputs and then 10 outputs. Great. So now I'm going to put this there and this there. And I'm going to train it on this shape. Add the points. Put this there and this there. And give it some rando thing. Add the point. Put that there and that there. And give it the opposite vibe. Something like this. Add the point. So if I post my points, I have 4 input vectors of 4 points each, and 4 output vectors of 10 points each. Great. I'm going to write my JSON. I'll call it my training2.json. And now I am going to go over here, and I'm going to run this again, but I'm going to change it to my training2. I don't know why. I guess I didn't press the button. I screwed something up. I am going to change this. The output needs to be 10. And I'm going to change these to 20, 10. That's fine. So I'm going to do that again. So I'm going to set the epochs, set the learns, set the layers. I forgot to do this. Let me just make sure those points are still there. They are. Write the JSON. My training2.json, replace, and run that training again. So when you're doing this, it's good to have your Python virtual environment set up, and much more accurate this time, set up in a terminal window and just kind of hanging out. So you can just pop over, press the up arrow, and rerun the Python trainings. Okay, so if we load our model, my training2, make sure it's the RTNeural one. This is the one you saved. Okay, so if we now move this around, okay, that seems to be working. But if it's not working, so we need to change this here to a pack with a K, and I believe, yeah, that'll work. So any of these points should be quite available. So that is how you modify this help file to do what you need it to do. This one's set up to send MIDI to VCVRAC for some synthesis. Okay, so I'm going to go over how to get RTNeural running on pure data. So when you download the files, it looks like this. That's going to go in, it can go anywhere, but I'm going to put it in the externals folder of pure data. Now I'm just going to put that in there. As far as I can tell, PD does not recursively go through the path. So when you open up PD, you've got to go into the preference or the settings, and then add this folder. So documents, PD, externals, RTNeural PD, and I've put the plugin and the plugins and the various help files in that folder. One more thing you've got to do. So once you've added that, you're going to quit out of PD. One more thing you got to do is you got to de-quarantine these .so files. They're executables, and macOS, at least on macOS, you need to do this. On PC, you don't need to. So in the terminal, xattr-c, and then I'm just going to drag in the folder and say /.so. /star.so. There we go. So that went through and it dequarantined the RTNeural and the RTNeural tilde executables. So now when we reopen PD, we should be able to make a new object, an RTNeural object, and go to the help. It should open up. So here we have a classic multilayer Perceptron example, and this should in the folder that we just put in the externals. There's some models that are downloaded. These are just various models that one that I've trained and others that I've found on the internet, or two that I've trained. And then in output there is use this folder essentially to do trainings of multilayer perceptrons if you want to. So I'm going to load mlp_training_rtneural.json. That's this file right here. This is you can tell that it's a JSON file in RTNeural format because of the vertical nature versus PyTorch, which tend to look like that. So outputs from PyTorch will look more like that, but that's what a RTNeural format looks like. So we're going to load that model, and it should do inference, right? So that's working great. So if we want to train the model, we're going to have to do a little bit of stuff in PD and a little bit of stuff on the command line. So if we click on this little MLP control window, we're going to clear the points. At any point we can post the points in, it'll post into the window, and right now there are no points in our training array. So we're going to set the epoch, so it's going to train at 5,000 epochs. Learn rate 0.001. That's an initial learn rate. The script that we are using has a variable learn rate, so as it gets closer to an answer, it will decrease the learn rate. And then setting the layers, this can be whatever shape you want, but the input is 2, the output is 10. So I'm going to have a hidden layer of 20 with a ReLU activation, a hidden layer of 20 with a ReLU activation, and then the output layer of 10 with a sigmoid activation. I think I did that. And we want to also bypass the model now, because if we're not bypassing the model while we're training, it'll be moving the sliders all around. So so internally in this object, in this external, there's an array that we can add points to. So we can set some points. 0, 0 is a pretty good point. We could set it like this, just so it's visually clear. Maybe something like 1, 1, and we'll add that point. Then maybe 1, 0, and we'll add this point, and 0, 1, and we'll add this point. Great. So if we post our points, there should be 4 points. And now we want to write the model. So we're going to write the file, and it uses a relative path. So when we go over here, I just wrote MLP training JSON, and this file it's a dictionary, so it could be in any order, but it'll be epochs, invals, layers data 20, 20, 10, learn rate, out vals. So all those values are in the JSON file as a dictionary. As long as those are there, we're good. The training needs to happen as of now in PD and Max. The training needs to happen on the command line. We should have our RTNeural Python folder already on the desktop. So I'm going to change directory to that folder. And we should have our virtual environment there. So we already made this virtual environment, and we're just going to activate it. Source venv bin activate. And now the virtual environment is activated. And in this folder, there is a script that is under MLP control, MultiLayer Perceptron control, MLP control train convert. So we're going to run that. So we're going to say Python MLP control train convert. And then the file that we're training is this one. I'm just going to delete this file so you believe me that it's going to get made. So if I run that, it's not super fast, but it is super accurate. Great. So we had a pretty accurate training. It should save the best training, not just the last training. Okay, so open it up. Looks like RTNeural format. And if we go back into pure data and we load our model, oh yeah, that was our shape. 1, 1. Like that, and then 1, 0 was that, and 0, 1 was the inversion. So that's how you train a network using pure data. So so I'm gonna close this up real quick, and just to show you that the models can run at audio rate if you want them to. And I'm going to open this up and open this up. So this one here is running at audio rate, and this one here is running at control rate. So if I load the model on the left-hand side, it's running at control rate. This is a different training than the one I just made. And then on the right-hand side, this one's running at audio rate. So as long as the DSP is on, if I load my model, yeah. So what you can do at audio rate is you can run the inference at audio rate. It's just going through that MLP of that size is pretty inefficient at audio rate, but you can put it in trigger mode. So right now I've just got like a random number generator that is triggering sometimes. I mean, you would probably want to use like an actual metro or trigger. So it will only do inference when it gets a trigger, right? The left-hand side is moving at control rate, the right-hand side is moving at audio rate, and the trigger, it only changes on the trigger. So that's another thing that's possible. In order to do that, you want to tell it the size is 2, input size is 2, output size is 10, but then the audio signal that you send it is actually 3 signals. The first input to the neural net, the second input to the neural net, and then the trigger. Finally, let's load up the RTNeural SC library. And if we quit out of PD, SuperCollider libraries should go in the externals folder. So when you go up to, you can't see the top tab, but when you go up to Go, hold down Option, and the library folder will pop up. And in the library folder, SuperCollider stuff goes in application support, SuperCollider. And I'm just going to put this in the extensions folder. Now, we also have to dequarantine the SCX file. So if we just go back and XATTRC, it's just this one file. Great. So in SuperCollider, now I'm in Visual Studio Code. If we recompile the class library, and if we type RTNeural and Command D, we have the RTNeural help file. There's all kinds of examples in here doing audio rate and control rate things. One thing you can do, this example here at the end is kind of fun. So we're loading up a synth that takes a Sawtooth wave and the mouse as inputs, and it outputs a variable oscillator. So I'll show you what I mean. Oh, gotta boot the server. So here's a Sawtooth wave right there. And if we load up the example now on the left-hand side, so if we show the scope, on the left-hand side we'll have a sine wave. Sorry, I'm using mouse Y. Up and down, bottom we have a sine wave. And as we go up, we go to a triangle wave, square wave, and a Sawtooth wave. And it's using a MultiLayer Perceptron to do that. In the SuperCollider RTNeural folder, in the help source, there's a MLP control tutorial, and I recommend you checking that out. So I'm just going to open it up. And if you go through it, it gives you a step-by-step on how to make how to train a model. One of the parts of this video is showing you how to train a model to be a fake adder, so a neural net addition. But I'm just going to show you down here. I've made kind of the classic MultiLayer Perceptron example, and it goes through. It basically makes a graphical user interface for training models. One of the things that's nice about the SuperCollider side of things is you can run the Python training on in SuperCollider, because you can run the command line in SuperCollider. I just need to make sure that the Python path. So yeah, in this help file, you want to make sure that the Python path is correct. So I am going to go over here. And I'm going to change this Python path right here to my desktop Python. And now the example should work. So it's feedback oscillator that's got some fun stuff going on in it. And it's got this interface. Now, if I just load a training, and in the tutorial there is a synth RTNeural.json file. So that is a training of the MultiLayer Perceptron in a shape that let's see, what is the shape? Yeah, 7, 11, 13. So input of 2, then hidden layers of 7, 11, and 13, or 7 and 11, and then an output layer of 13. But I'm going to open this training, and we get So it sounds pretty good, and it works pretty nicely. So to train with this thing, and you can go through the code yourself. But if I clear the points and turn the predicting off, then moving it around will do nothing, right? So I'm just going to train it with some random stuff. So make a random sound, like it. So I'm going to clear points, add the point, make another random sound. Yeah, can't go wrong with this one. Add the point, make another random sound. I like that one. And one more. Okay, so once we've added all the points, then we're going to save the points. And we'll just call it we'll call it synth video.json. Train from files. So it should do the training. So if I say synthvideo.json and I say open, when it says wait for the done message and that's all it says, that's a good thing. It's going to take a second to run this training. And when it does run the training, it'll give you all of this in one go. So if you do the training on the command line, it'll print these out as they go. For some reason, that doesn't happen in SuperCollider. So this did 2,000 epochs, came up with a pretty accurate answer, and then wrote the trial. Wrote the file. So now I'm going to load the training, and I'm going to load synthvideo_RTNeural, my training, and we should have the training. So obviously you can do this with Flucoma NLP regressor, fluid NLP regressor, but this is just a different approach if you want to deal with Python. Okay, so we're going to make an adding machine using the RTNeural training on a multi-layer perceptron. And so starting off, RTNeural in SuperCollider will make a default training dictionary with values that we don't want to use. But if we make that dictionary, we can look, and if we do a .keys do, so it's a dictionary, so we can look through the keys and see what kinds of values are in the keys. So down here, yeah, so we have layers data, and that says what kind of layers we have. So the default is a, 4 hidden layers plus an output layer. And the hidden layers are 3 with a ReLU activation, a 5 neuron layer with a ReLU, 7 neuron layer with a ReLU, 9 neuron with a ReLU, and then 10 output neurons with sigmoid. That's not going to work for what we're doing, so we need to replace that. It also does dummy output vowels and input vowels. And something to notice here is that output vowels, the key output vowels, has an array that is made up of arrays. And in this example, our outputs are only going to be one value, but they still need to be arrays. And the input vowels will be arrays with 2 values. So let's change this layers data. So I'm going to make this equal to an array with 100 ReLU, and then another one with 100 ReLU. It's probably way too big, but it'll be very accurate. And then one with 1 sigmoid. So, didn't like that. So those need to be strings. They need to be strings. And now And now the layers data, if we look at this, the layers data is correct. It is ReLU with 100, ReLU with 100, sigmoid with 1. So that's the shape we want. We probably could do whatever kind of shape we wanted, but that is going to maybe work well for our adding machine. Okay, so now we need to add values into the array to do the training. And so our invals, we're going to make that a list. So we're just going to make it an empty list. And our outvals are also going to be an empty list. So what I want to do is make an adding machine. So we're going to make something, we're going to teach a neural net to add. And so I'm just going to make 5,000 values. So we'll say invals, or we'll say var temp equals an array of 10.rand and 10.rand. Actually, let's make it 11.rand. That, I think that only goes up to 10. Yeah. Right. So between values between 0 and 10, basically. So that's our temporary value, and we're going to add it to the invals array. But it's a neural network, and the inputs and the outputs need to be between either between -1 and 1 or between 0 and 1. And in this case, since we're using a sigmoid on the output is going to be between 0 and 1. So let's make the input also between 0 and 1. So we're going to add temp, but then it'll be temp divided by 10. So that'll be values between 0 and 1. And then for outvals, we're making, it'll be an array that is temp dot sum divided by 20. Right, so the output should have values between 0 and 20. So to round that, or to normalize that to between 0 and 1, we divide by 20. We've added the two values together and divided by 20. Great. So that gives us these two arrays. And now we're going to add these two, or make these two arrays the arrays in our dictionary. So if we look at that again, invals points to an array of arrays. And this will be an array of arrays. So dict at invals equals invals. And dict at outvals equals outvals. Is that right? Yeah, so if we now look at our dictionary, it has this invals. Now it has it as a list. Let's see if that's going to work for us. I believe it will. Okay, so now that we have our layers data is right, our outvals is right, our invals is right. Epochs is set to 5,000. That's fine. Good learn rate 0.001. It will. It's an optimized learning rate, so it'll change the learning rate as it learns. But this will be the initial learning rate. So we need a path for the JSON file that we're going to save. So I'm going to go over to my desktop. This is where the file that I'm working in. So we'll use that path. So I'm in VS Code. So I'm just going to drag this into the terminal in VS Code, and it'll give me the path. In SCID, you can just drag it into the IDE. So not sure what happened there. But we don't want it to be .scd because that would save it over our file that we're editing. So that would be bad. So adding mlp.json is the file, is the JSON path. And so saving the JSON file requires the JSON libquark. So if you don't have that installed, you can just do quarks.gui. And you just check the box. Now I have it installed right here, so I don't need to reinstall it. If you need to reinstall it, you just check the box, recompile the class library, and it will install that quark. So it is installed. Now let's see if it will save that correctly. Yeah, so it just will convert, looks like it will convert the list into an array. That's very nice. So if we go over here now, we should have a JSON file, and it has epochs 5000 invals are two-dimensional arrays. And if we scroll down a long ways, then the layers data, it's a dictionary, so it could be in any order. Learn rate outvals, so the outvals are in fact one-dimensional or two-dimensional array, but of single values. So we have our JSON, which has the necessary information to train our model. Now we want to run the training. Because we're in SuperCollider, we can run the training in SuperCollider, because SuperCollider can work on the terminal, which is very nice. So this is my RTNeural Python directory, so just going to drag that in there, copy it. So our Python path will be this directory. So we have a JSON path already because that's where we saved our file right there. That's our Python path. Now, RTNeural train MLP. So this will look at the correct Python program to train the multilayer perceptron. So in here, we're assuming we've already set up our virtual environment. So the virtual environment folder is there, and it already has the pytorch and tensorflow and keras installed. If we have Onyx script installed, that's also nice, because it'll output an Onyx file and a pytorch training. So yeah, so this is where this directory is. That's what we just told it. And in here, we're going to run the MLP control train convert. So what it's going to do is it's going to do the training on the multilayer perceptron, and then it's going to convert it to RTNeural format, which is keras format. Great. So if we run this, it should work. Let's see if it does. Yeah, so it's taking a second, which is good. If it happens really fast, then you probably did something wrong. Shouldn't take too long. The SuperCollider terminal will post everything that the terminal, that running the program in the terminal would post, but it will only post it at the end. So now it did it, and if you did this in the terminal, it would step through each of these and one by one. In SuperCollider, it just posts them when it's done. But the training has a very nice, very little loss. So that is now our training. And if we look over into our folder where we put our adding MLP.json, it should now have adding MLP underscore RTNeural JSON. So we have a big honkin' network with 200 different weights, sets of weights. And yeah, so let's make a synth-def. So unlike Max or PD, you know, the SuperCollider needs to be running on the server. So, but it can be, this runs at control rate. So synth-def is, and we'll call this MLP adder. And I'm going to put in, this is just going to be really simple. I just want an RTNeural.control rate. The input array, so I'm going to use named controls here. We'll call it, yeah, we'll call these invals. And that's going to be .kr. I'm going to give it an array. So I'll just give it 0, 0. So that's going to be, that's where we're going to be able to set our input values. If we look over in the help file, the next thing we need to give it is the number of outputs. So that's going to be 1 because we're adding 2 numbers and we're getting 1 back. The ID, let's call it adder. So we could have multiple RTNeural instances in our synth-def, but in this case, we only have 1, but we're still going to give it an ID. Okay, and .poll. I'm going to slow down the poll to only once a second, and the synth will have an output of nil. Okay. So it was happy with that. Let's make a synth called A. MLP adder. Cool. 0 plus 0 is 0. That's nice. So yeah, so now let's load the model. Is that the correct? No. Okay. Any complaints? No. Let's look at that. No, it loaded it fine. So it should be able to do inference. So we're going to say a.set, and we're going to set the invals to 11.rand, and then divide it by 10. Let's post it first. Post line. Okay. So that's giving us the number between 0 and 1, which is what we're expecting. So let's see if we fix this up here. So the output should be times 20, should be, and we'll put that into a parentheses. So I need to stop the synth, reload this. And 9 plus 3 is 12. 0 plus 7 is 7. 9 plus 2 is 11. 4 plus 3 is 7. Now, something that might be cool here is we only trained it on integers, but let's see what happens when we give it floats. It should be relatively okay. So 4.18 plus 8. Yeah. Here, I'm going to run a couple of them and then stop the scrolling. So, yeah. 9.37. Yeah, that's pretty good. It's pretty good, not bad. 6 point... Why is it giving me difficult ones? So, yeah, that would be 7. And that's 14. That is pretty close. Here's a nice, easy one. So 4.26. Well, that's 7. So, I mean, it was pretty accurate, even though it was only trained on integers. So, yeah, that's a little MultiLayer Perceptron trained on adding two numbers together. Pretty silly use of a neural network. Okay, in this video, we're going to talk about distortion models and like amp cabinet models. And if you look in the RTNeural Python folder, there's a folder called AGAM reduced. So in here, you have a version of Alec Wright's automated guitar amp modeling repository that is reduced but also expanded. So it is reduced in that it is much simplified. It only deals with GRU models or LSTM models. But it will allow you in things that his library doesn't allow you to do. It'll allow you to train on the Mac GPU, also on a CUDA GPU, although I haven't tried that out yet. It'll train on audio that's either at any sample rate, and it'll train at any bit rate. So it'll load kind of any file now, but it only does GRU models and LSTM models. So in there is this amp dist models. There's just some models from the internet that are open source and downloadable. One of them we have here, we're going to look at DoD American Metal gain knob. So this is a model that is part of the Proteus library. And I'll show you where to get some Proteus models in a second. But when you download a Proteus model, it looks like this, and that's just a standard PyTorch training. So it's the JSON format of a PyTorch training. And up at the top, you have some information that is important, like the input size. So this is a model that was trained not just on audio, but also on a gain knob. So he trained it to adjust the neural net based on the gain knob. Skip connection, this is actually important. When a neural network is trained with a skip connection, the audio of the input audio is added to the output before it's checked for accuracy. So that means that it's expecting that audio to be added back in to sound correct after when you play things back, and you can hear the difference. Output size in audio is generally going to be 1. Unit type LSTM. So this uses a long short-term memory model. And then number of layers, 1. Most of these are use 1 layer, but we can load layers, things with 2 layers. And then the size of that layer. So it's a 40 hidden layers to this LSTM. So that's what it looks like when you download it from the internet, and this is a file that's been converted to RTNeural format, and I'll show you how to do that in a second. And a lot of the same information is here. It's just in a different shape. Also, RTNeural format is in Keras format, TensorFlow format, and these are in what I downloaded was a PyTorch model. So let's look over in SuperCollider first. So I have a buffer, and I'm going to play the buffer. It's a steel pan playing Stairway to Heaven. And here's our synth-def. Couple things. We're playing a buffer, and then the gain is at audio rate. So I'm using the mouse. Mouse only is at control rate, but I'm converting it to audio rate. And the reason for that is I made a design decision with this ugen that all inputs would be audio rate. That will allow you, if you want to do a training on 2 audio rate inputs, Well, you can do that, and it'll work, whether you have control rate inputs. So something like a gain knob is really a control rate input, and that's how it was trained, but we're converting it to audio so that it works in RTNeural. So in SuperCollider, you have to put the two inputs in an array, and this is because we don't want to use multi-channel expansion. We want the plugin to work whether we have 1 input, 2 inputs, 5 inputs, 20 inputs. We tell it how many outputs we want, and with the number of inputs and outputs here, it'll know how big of or what kind of neural net to make, the shape. If you try to load a trained network that is not that shape, it won't load it. It'll just say failed. So in SuperCollider, you need to, if you want to have multiple of these in a synth, you need to give it a label or an ID. And this one, it's just a symbol, and it's called this one. And I'm going to use that down here when I set the model. So bypass is 0. Sample rate. So I know that an RTNeural model, a Proteus model is trained at 44,100. So I'm telling it that the model is at 44,100. What that allows us to do is, even if we're running at, 96K, internally it needs to do the inference at 44,100. So it'll take the audio, convert it to 44, take the 96K audio block, convert it to 44.1, do the inference, and then convert it back to 96K. And then here I'm adding the input back in. That's to this idea of the skip connection. So we need to add the audio back in for it to actually sound correct. And we'll listen to the difference. It's not that big of a difference. Like, it still sounds good, but it's expecting that. So if I press play, and now I'm going to load this model. So I choose the path, and now I'm going to set the synth, give it a ID, and then give it the model path. Now we know this is supposed to be at 44.1. That sounds really good. But if we switch to 48, it'll sound a little different. It doesn't sound too different. And then if we switch the amp of the input, it'll sound a lot thinner. So we want to mix the input back into the signal. I was just controlling this here to hear it correctly. Now, some models, like A to X models, their models are already in RTNeural format when you download them. So I should be able to load this. Yeah. And it loads. So that's when you download an I to X model, it looks like this, and it's already in RTNeural format. They've chosen to save their models that way. So great. So to confirm, let's look at these things in Max and PD. So in Max, we've got a classic beat, and I don't know if I load my distortion now. If I change the volume of the level of the gain knob, down here it sounds one way, and up here very different. Now I realized that I screwed this up. I really should have I should add the signal back in. Will that work for me? No. And if I do that, yeah, it should sound a little better. It's hard to tell, but yeah. So Max, the things in Max and PD is you need to tell the neural network the size of the inputs, the size of the outputs, and then the sample rate of the neural net right here. So if we go over to pure data, very similar. So this is just using a sine wave, And if I turn on the DSP, why are we not hearing that? Oh, there we go. Weird. All right, so there's the oscillator coming in, and if we load the model, it gets distorted. So you can see it's the same as Max, almost looks identical. So 2 inputs, 1 output. And in both Max and PD, I need to convert this control rate to a signal before they're snaked together. Yeah, actually that's a good point. So in Max, I'm using MC pack to pack all the input signals, and then those go into an RTNeural, and then we unpack the outputs, even though there's just one. In Pure Data, same thing, but Snake is the version of MC.pack, and so we take the oscillator input and the control input, and we snake them together. So now I'm going to show you how to train a neural net to do something silly, which is to turn a sine wave into a Sawtooth wave. So this might not be all that useful in the real world, but it shows the power of these neural networks. So let me just show you in Audacity these two waveforms. So what we have to train any neural net, we need an input and an output. And in the case of audio-based neural networks, we want an audio input and an audio output. And so our audio input is going to be a sine wave. Now, there's these are a second long, right? So this is at 1 hertz. There's 2 of them, and then it slowly goes up to about 22,000 hertz. So it's a single sweep over 9.5 seconds. And the target is going to be this Sawtooth wave. And also notice that the phase is perfectly in line. That's really important when you're training these audio networks, that the phase is aligned. So even if you're training like distortion model, you want to make sure that you didn't add some kind of delay to the effect that you're trying to do. You want things to line up. It's good to put like a onset or an impulse in the audio file so you can line things up. Okay, so those are my 2 audio files, input and output. They need to be the exact same length, same number of samples, otherwise it will complain. So I'm going to close this, get out of Audacity. And in AGAM, I'm just going to start with a deactivated virtual environment. And in order to activate that, I need to be in the root directory of the Python, RTNeural Python. So I'm just going to go back and, what did I do? I'm going to go back to here, and then I'm going to engage the virtual environment. And it's engaged, and now I'm going to go back into this AGAM reduced. So in here, there is a file called distmodelrecnet.py, and that file is what we're going to run. That's the script we're going to run. If we open this file and look at it, there's all the imports at the top. Make sure SciPy is imported in your virtual environment. It's going to need that. Just pip install SciPy, and then it shows you all of the parameters that you can use to train your model. So a way to see that is you can say Python and then this file, so dist model recnet.py, and then -h, so for help, and it'll give you this output. So another place to find this help is in the README of the AGAM folder, and at the bottom, this has the help, but then at the bottom it has a sample script of how you might want to run it. So I'm just going to copy this because we're going to want that to help us out. And that'll obviously give us an error, but that's fine. I just wanted to see these parameters. So let's go through these. So H is to get the help. Dash in will give you the in file, so the name of the input file. So that's the file that we said was our audio input. So in training data, RNN saw the audio input. The target file is the audio output. So the target that you want. So you want to turn this into this for the distortion. The out file is the training. So that's the name of the training, like gru_16.json. The epochs is the number of times you're going to go through the training, the number of loops that you're going to do in the training. It's set to 500 by default. The nice thing is you can set it to 500 and let it go, and if it gets stuck at some point, then you can interrupt the training and it will save the training as it goes. Whenever it gets more accurate, it will save the training. So learn rate, has a default of 0.005, and it changes over, so it's initial learn rate. It updates as it goes. So it should, the learn rate will get smaller and smaller so that it can kind of hone in on the closest answer that it can get. Initial length, we're not going to worry about that. UF, we're not going to worry about that. Pre-filter, this is important. So in this case, we do not want to filter the input audio. In the case of a distortion model, we do want to filter the audio because the low end doesn't get distorted like the high end does. The high end is where all the distortion happens. So you want that on high pass for a distortion model. For this, we have, that first, waveform is at 1 hertz. If we did a high pass, then we would get rid of that and it would be stupid. There'd be no reason to do it. So in this case, this is a training where we don't want to use that pre-filter. Input size is mono, output size is mono. Those are the defaults. Number of blocks, 1. So that's the number of blocks in the neural network. So we're going to do an LSTM or a GRU network, and there's how many blocks of hidden layers there are. So default is 1. That seems to be what people use. Seems to get just as accurate results as 2. So we'll leave it at that. Hidden size. So default is 40. So this is the size of the neural network, these recurrent neural networks. That's how it's labeled. And we're going to do 16 for ours. LSTM, long short-term memory, or GRU. So these are both different shapes of recurrent neural networks. We're going to stick with the GRU on this one. The LSTM will train faster on the GPU. The GRU seems to train much faster on the CPU, so we're going to do that. This is Sam from the future. I made a mistake when doing the training here, and I set the skip connection to 1, which will result in a messed up training, which is actually good because we will see the messed up training and you'll understand why you don't want the skip connection to be set to 1 when you're doing this kind of transformation. Use GPU is whether we use GPU. So I'm going to say Python dist model recnet.py in, and I'm just going to make it easy on myself. I'm just going to drag that in. Doesn't matter if it uses a relative path or not. Tar, the target, dragging it in. The out, I'm just going to drag this in again and edit it. So this is going to be GRU_16. Yeah, we'll just overwrite. It's not a big deal. That's not a training that I care about. Out. HS, so the hidden size. We're going to do 16. This will be a efficient network. Then UT, so RNN format, we're going to do this as a GRU. And because it's a GRU, we will set the GPU to 0. And so it'll train on the CPU, and this will be faster. Yeah, so notice that as it's going, it's much faster than the CPU, the GRU. I ran it previously today on the GPU, and it was very slow. But the LSTM is the opposite. So notice that it made this file called GRU_16_best. So every time the network gets more accurate, sorry, is the word, it will update the network. So somehow it was modified after the current time, but that's okay. Oh, right. So I'm sorry, I'm looking at the wrong file. Yeah, so it was just updated at 8:18, and you can even watch it being updated at this point because every iteration, every epoch is far more accurate. So I'll let the screen scroll, and I'll be back to you in a minute. Okay, this doesn't happen too often. I'm going to interrupt that. This training got stuck, and it got stuck at a number that's not ideal. I'm going to just run it again, and I guarantee it'll be better. This happens sometimes, doesn't happen that often. I'm glad it happened while I'm showing you this, so you know that can be a thing. Okay, you can see there that it got to 0.029. I've had it get below 2, so 0.02, so that's not a bad training. I should have saved the one that got below 0.02. So if we go over to SuperCollider now and we load this puppy up, let's see here. We can't load it up. We need to convert it first to RTNeural format. So now we're going to run Python, and we're going to run this mammer jammer, the AGAM GRU to RTNeural, and we're going to run it on our training. Oops. I need that to say -F, so the file that we're going to convert, and it should run this pretty quickly. Yeah, and it outputs the GRU model and the PyTorch and the Keras to make sure that it's accurate. It was accurate, and it made a model for us. So let's see what that sounds like and looks like. So it's just a sine wave in, right? Yeah, just a sine wave. It needs to be at full volume. I was tricking myself. I had put this at not full volume, and the output didn't make any sense. It needs to be all the way between -1 and 1. The RTNeural is getting the input, one output, and that's the whole circuit, really. So let's make sure this is the right path. Now, what's cool here is, ooh, that is a wild one. Okay, so if you train it with a skip connection, it's going to make an output that is distorted in the shape of the sine wave. So if we make out equal out plus in and run that, now we get a sawtooth wave that we want. So training with the skip connection set to 1 on signals where you want the exact output to be, you don't want to have to add the signal back in. You don't want to set the skip connection to 1. So in this case, we set the skip connection to 1. It gave us a signal that needed the signal added back in. So I'll take it back out again. And look at that weird shape, right? Because it doesn't have the sine wave added back into it. So what we really want to do in this situation is run this training again. And we're going to run it. We're going to change the output to skip connection. And we will make the skip connection set to 0. And see what happens there. Okay, it seems to be stuck at about 0.0255. That's pretty good. So we're going to stop it, and then we're going to convert that so SC best. Why did I put that there? SC, so skip connection, the best one. All right, let's see what this looks like. Go back to the SuperCollider code, and the thing we're gonna load, yeah, is this one, the SC best. So yeah, so it's outputting. Let me just make sure I don't have the one with the input added back in going. Nope. So yeah, so when doing something like this, which you probably don't want to have the skip connection engaged, because you don't want to have to add in the signal back to the audio. But when training a distortion model, you might want to, because it will train faster. So we might want to go to the internet and get some trainings that have been made. Now, these have been made for specific plugins, but they can be loaded by RTNeural. So this Tone 3000 web page is one place to get them. Another place is on the GuitarML web page. So here, if we want this Mesa Boogie Mark III red stripe, that's an amp head capture. So it's just modeling the amplifier head. So we can click on that. Now this is an A to X training. And if we download it, let's just look at that for a second. So this gives a bunch of different trainings. So clean with a standard size LSTM model, high gain, crunch. So if we open up crunch, we can look at it. Now, interestingly, it's there's some in shape is missing, but all we care about is this. Then it's an LSTM, and it's only 16 layers, so it's a pretty thin model, very efficient, and if it sounds good, that's all that matters. So if I go back into my SuperCollider code, now the difference here, and I'm going to give myself some space, is that this model runs at is just one input. So I'm going to make RTNeural dist, get rid of the 2D, and rather than having input and gain, I'm just going to have input. We still want that in an array, I think. So if I load that, and just going to copy this code. So if I take this download and I load it, it should work. So now I know that the A to X models are trained at 48K, so I'm going to change that. Let's see if we change it right here. So those models we can use directly, and it's no problem. If we want to get a model that we can't use directly, for instance, instead of an A to X model, we're gonna load a Proteus model. So this is Keith's trading of a tube screamer, center tone knob settings. So this is a two-dimensional one, so audio and gain knob. Let's download that. Great. And if we look at our downloads, I open this up, it has the pytorch looking pytorch format. So if you get a pytorch format, we can convert it. And if you look in the RTNeural Python folder, in AGAM reduced, there is a couple scripts in here, and two at the top here are AGAM grew to RTNeural, AGAM LSTM to RTNeural. Now I know that his models are all LSTMs, but you might want to look. It'll just fail if it doesn't work. So in pytorch, sorry, not in pytorch, in the terminal. So I'm in my root directory. So I'm going to change my directory to RTNeural Python. And so the root directory of the RTNeural Python folder. And the reason I'm doing that is because I want to activate my virtual environment that we've already made. So I'm going to say source venv bin activate, and it'll activate my virtual environment. And now I want to change my directory to agam_reduced. So to convert a model from an LSTM PyTorch training to this Keras RTNeural training, all we need to do is run the script. So we'll say Python agam_LSTM_2. I could just drag it into, but I figure why not type it out. RTNeural.py, and then it's looking for the file that you want to convert. So if we say -f, then we can drag our file in, and it'll take a second. Didn't take that long. So it does some inference on the PyTorch and the Keras models to check that they're the same, so that the output is the same and the output is identical. So now we have the RTNeural model. So I can go back into my SuperCollider code, and I'm going to go back to my 2D model. So if I load this, and I'm going to, that's going to be my model path. And if I load it, it sounds very nice. So that's a really easy and convenient way to convert trainings. So I'm going to show now how to use the embedded script to train a neural net that's a distortion. And so first thing I'm going to do, if you go to the A to X Google Colab, there's an input.wav file. So I'm going to download this. This is what they use for training, and so this is what we're going to use. You can use anything. You could use any kind of sound, but you can see there's a couple. You'll see there's a couple features of this that I think make it unique. So I'm going to open it with Audacity. See if we're. Yeah, so they have this like pitch shifty thing, this like vary speed thing going on, and I'm sure they have figured out why you want that. Now we'll be able to hear the effect there. So part of the reason I also wanted to look at this, to use their file, is it is 48K and 24 bits per sample. So that's a high quality file that we can load in this version of the automated guitar amp modeling. So I am going to go to Effect, Distortion, and every time. Effect, Distortion, Hard Overdrive. So I'm going to apply this, and you can see that we get a hard overdrive. So I'm going to export this. Wow. And I'm going to put it in this folder, the same folder. Well, I'm going to put it here. I'm going to make a folder called dist. And dist, we'll call that input.wave. No, sorry, not input.wave. That's target.wave. Target.wave. Now notice I did something really stupid there, and I am going to export the audio again, and I had it on 16-bit, and I want it on 24-bit. Great. Target.wave. Replace it. Great. So I want to make sure my target is at 48K 24-bit. Great. So I'm going to move the input into this folder as well. And basically we're going to do the same thing. The thing is, I'm not going to let this run. I'm going to do it overnight and look at it in the morning. So great. So I'm going to run Python, and we are going to run dist model recnet, dist model recnet.py. In is going to be input. Ooh, let's type that correctly before we do that. Tar is going to be target. Out. LSTM. Let's do 50. JSON. We want to make sure. Let's see if there's any other settings I want to be sure to grab. Learn rate's fine. Pre-filt is on by default. That's good. Input size, output size, num blocks, hidden size. We already HS should be 50. And skip connection is on. use GPU is on. Unit type by default should be LSTM HS50, but let's do it. Let's specify it anyway. So UT is LSTM. Okay, so this is going to take much longer because it is a much larger neural network and it is a much larger chunk of audio. So if I get this going, it says it's using the MPS, which is nice, but it should train much slower. Okay, I let that go for a little while. It didn't really take that long. It took like 2-3 hours. The training ended up being pretty good. So 0.0065, and it saved this one here. I started a little after 8, so it took about 2 hours on the GPU on the Mac, and that is our training. So we need to convert that. So let's use our converter here. Just delete the old file. So again, that's Python, and then the AGAM. Ooh, we're going to need to change that to LSTM to RTNeural, because this is a LSTM model. Run the conversion. It's all good. So let's grab that the path for that. So if we go into SuperCollider, and we're going to use this path instead of that one. So if we play this, now, you know, to hear that correctly, we should add, since we use the skip connection, we should say synth equals synth plus in. Whoops, that is too loud. I see why. So when we're adding it back in, it's just much too loud here. So let's do that. Cool. Let's see if that sounds anything like what Audacity does to the sound. So this is the same training we used, or the same distortion we use. Okay, it's good, but it's very loud. And hear that. Sounds pretty good to me. So if we go over to Max and we want to use the same thing, this is the example that's provided, and all we need to do is drop that model into here, and it should load. And now when we play it, I'm going to put it on loop. Awesome. And just to show you how to load that into pure data, I don't have a sample loaded, but we can copy that path, maybe from SuperCollider. Go over to pure data, put that in here. It might not like the quotes. Let's get rid of them. And this should also work. And it's loaded. So that's just a sine wave, but kind of a neat distortion. If you look at it, it looks just like a basic fold distortion, but with a nice soft edge.